So yeah, first of all, thanks a lot for liking my poster and giving me the option to present my work also in this different setting. I threw something together from different slides that I had on hand, so let's see how this goes. Basically, my poster presentation was also a summary of my past research work, my current research work, and hopefully my future research work. So let's see how I can get a storyline out of this. I'm from KIT, Karlsruhe Institute for Technology, and I started my PhD like 8-ish months ago, so not too far into the PhD process. And I will present on reinforcement learning for agent-based electricity market simulations. And basically, I want to get into a little proof of concept. So first, I'm going to tell you why I want to do that or why I think it's a good idea to do that. Then the proof of concept, and then a little evaluation discussion. So let's get started. I come from a system perspective. As an industrial engineer, I first tapped into the whole energy topic with energy system simulation. So there, the overarching question was, how do we get our energy green? How do we do this system transformation? And in general, there are two approaches of solving such a question. Either way, you use an optimization. So typical top-down approach, you minimize the overall system costs of your system. And according to that, you dimension your different resources, such as transmission capacity or power plants. This, however, assumes that every participant, every power plant behaves according to this overall system goal, so minimizing system costs. The question is, do they actually do that? Does an individual power plant care whether or not its bidding is system optimal, or does it not care about its own profit? Right, so they do not necessarily care about the system optimum. They want to maximize their profit and they do not behave optimal. Why? Because they don't have perfect foresight, of course. We have some uncertainty. We heard a lot about it in the first talk as well. They do not necessarily have rational behavior in an economic sense. And like I said, they care for their own profitability. In the first overall system optimization I worked with, there were some power plants that were built, gas power plants, and they would be dispatched. But in the end, they do not even earn their money back for the investment. So not really something that we would see in real life. Hence, the other idea is to do an agent-based simulation, so bottom-up approach. We look at each agent and see what would they do in order to optimize their system, their little system. And then model, for example, non-rational behavior as well as imperfect information or information asymmetries even. And then all the bits of these different agents, they evolve to the overall system behavior in a market, right? Just a simple merit order. Question is, in all agent-based simulations, how do they behave though? How do I model the actual behavior of these different power plants? And I want to give you a quick recap first on how this is currently done in agent-based simulation. This is also where I'm coming from with my research. So I worked in agent-based models for like 2-ish years also during my master's. And what is currently done in the big models is that you have some market forecast. Maybe it's weather, mostly it's demand and electricity prices. And you would give that to your simulation model. And there you have a little agent. Let's assume it's a battery. And the battery sees this demand and electricity prices and tries to bid into the market with rules that I define as a modeler. You could, of course, also use optimization approaches for each agent, but then it gets large, very, very quickly, very, very large, such a simulation, because then for every power plant in your system, you would have to solve these tiny optimization problems, which can get very time consuming. So what is usually done in agent-based models, you use some heuristic. For example, for a battery, if the price is below a threshold, I charge. If it's above a threshold, I discharge. But that is something that I, as a modeler, come up with. And this works fine. If I have one battery, then it makes its bid. Everyone's happy. But what if I have a lot of batteries? They all seem the same price forecast. They all see the same price forecast, and they all have the same bidding strategies, so they all do the same. And if I have like enough storages in the system, this will highly distort my complete simulation results. Like you can see, we now have P2, which is very different from P1. And the question is my decision strategy still smart in that case? Because these heuristic cannot anticipate my own price impact if you do it very easily. And this sounds ridiculously stupid, but it's how it's done currently in agent-based simulation. in order to keep really the computational burden down, because you want to do it for a very long time horizon, let's say up to 2050 hourly resolution. So that is the way to go now if you want to model the whole system. And the idea is, for the project that I'm working on now, we want to replace that. So we don't want the modelers to assume the bidding strategy, but we want the individual agents to assume their bidding strategy themselves, and that is done in the project Assume, which I'm working on. It's a project where different research institutes are working on, also Uni Freiburg as well as the Fraunhofer Institute. And we are working on an open source toolbox that then has reinforcement learning. Learn smarter bidding strategies than the heuristic in place currently in agent-based simulations. So a little bit more about Assume. Reinforcement learning, I don't think I need to introduce that, right? We have an environment, has a state, then the agent chooses an action, and then we have a reward. Now we have multi-agent reinforcement learning, so we don't have one agent, but very many. And they learn by interacting with each other. So you just let them play multiple rounds, and then they learn inherently what would be a good behavior by interacting. And in this Assume, the goal is to develop this open source energy market simulation toolbox that has then adaptive bidding strategies using reinforcement learning. And we currently did the requirements and model interoperability. We also did the model development, and we are about to finish the reinforcement learning integration, at least partially. And then with this toolbox, we want to enhance the analysis of agent-based simulations in 4 ways, basically. We want to enable testing out new market designs, so that I don't, if I now want to test out a new market design, I also have to come up with a bidding strategy that remotely makes sense for each of the agents. So what the process is, I model something with my bidding strategy, I see the results make no sense, then I model a different bidding strategy, results still make no sense, and so on. It's an iterative process. And with reinforcement learning, we could test out new market designs in a way more sophisticated fashion, so to say, sophisticated. We also could evaluate market misuse, because reinforcement learning in such a setting, in such a multi-agent setting, has shown to be able to depict strategic bidding, as well as the use of market power, actually. So we could evaluate market misuse for new market designs, and also analyze the impact of sector coupling, of emergent dynamics, and new parallel markets and their dynamics. So that's the idea. And I brought a little proof of concept from one of the colleagues that is within this project. And basically, it's a German electricity market simulation. So unit-wise, every power plant is one actor that is bidding on the market. And we have different bidding strategies for all these agents, and all the pumped hydro storages were equipped with a reinforcement learning bidding strategy. So that were quite many agents. It was like 40, but we also tested it with like 150 agents. Currently in literature, you only have 14 max. So that was quite the gap to this proof of concept. And then they decide on bidding all based on the same price forecast. And I'm going to show you some results. So here we actually used an optimization-based bidding for the heuristic. And you can see in those results, we just picked like 2 random storages over here, that the results for the storages are pretty much the same. I mean, how could they be different? They get the same price forecast, they get the same optimization to bid in the market. So surprise, they do the same. However, then we have so-called avalanche effects that I also talked about for these storages in the introduction. And that is a problem that is encountered by many other agent-based simulation as well. When I was on a little conference with other agent-based system modelers, they were all talking about these avalanche effects. And then we came last with Assume, like, well, we have the solution. That was a very nice occasion to present this toolbox. And the solution looks somewhat like this. So now all the hydro storages have different reinforcement learning strategies, and they learn to exploit their own niche, so to say. So first of all, they anticipate their own price impact that they have on the market. We could show that with reinforcement learning. And the smaller storages now use different fluctuations in the market. So they don't go for like the overall price peak, all of them, but maybe for the price peak in 2 hours, not for 2 days, for example. And like this, the storages actually could find a profitable dispatch in comparison to the optimization-based, where they actually distort the market so much that they were unprofitable in the end. So as a little proof of concept. The question, however, remains is, how do I know if this bidding strategy is any good? Because with reinforcement learning, you would just see some convergence behavior of your reward, and then it converges at a certain value, and then I can look at the bidding strategies, but I'm not necessarily sure why, why it does that, or whether or not this is better than what it has done like 2,000 iterations before in the converged setting. So the idea, and also of my dissertation, what I'm very interested in besides developing this toolbox, is how to evaluate then the decisions made by market agents trained with reinforcement learning. Because while there is a lot of interest in the agent-based community on using reinforcement learning in the first place, all of them have the same criticism. I cannot interpret this so easily as with the heuristic that I came up myself with in the bidding. So the idea is, for multiple market player, the behavior of the agents equals the market results, right? I don't have, if I test out a new market design, I don't have any historic market results that I compare it to. If I do it in a setting today, I just model everything with reinforcement learning and see, okay, now we converge somewhat to the prices that we see in reality. But as soon as it's a new market design, or I look into the future, I don't have these historic results anymore, so it's harder to elaborate on. And optimum would be, of course, the equilibrium model, so the game theoretic optimum for this agent-based problem. But if I could solve that, I wouldn't use the agent-based simulation in the first place. So we can't. The idea, and that's also something we want to implement in Assume, and that would be then the future research, is we heard a lot about trustworthy AI concepts yesterday, to integrate some of those, for example, the SHAP toolbox, or also converting the bidding strategies that the agent find into decision trees. And such decision trees are now interpretable by me again, by the modeler. So with my domain knowledge, I can say, okay, this decision tree somewhat looks like it makes sense, and I can understand what the agent actually learned. Or, of course, compare the simulation results with reinforcement learning to the rule-based strategies that are currently employed for the multiple market players. Right, that is integrated in Assume, already said that. For one market player, that would be the other idea. So pick one market player out of this multi-agent concept, just really evaluate how good reinforcement learning performs for this one market player that decides on its own bidding decision and has no market impact. So we say it's a price taking, the market is given, and I just look at this one market player. And actually, this one market player faces a typical sequential decision problem under uncertainty. So what is the sequential decision problem under uncertainty? That's a name that Powell framed, someone from the stochastic optimization domain, that tries to summarize all the different problems from different domains that somewhat make a decision sequentially under uncertainty, as the name says. And we could then compare the results that reinforcement learning as a solution method to sequential decision problems find with other solution methods from stochastic optimization. And that is basically what I'm going to talk about in the next two slides, to quickly give you an insight into what I'm planning on doing. So what is this sequential decision problem? Well, in Germany, at least, just a very simplified setting. We have different markets on which we want to place our bids. So we're now again in the bidding theme, as in the last talk given yesterday. I have to decide in the morning whether or not I want to bid on the balancing reserve auction. I don't know if I'm going to be successful or not, but I needed to know whether or not I want to be dispatched in the spot markets beforehand. Because if I'm not dispatched in the spot markets, I also cannot really provide balancing reserve, because my plant has to be running, right? So that is, for example, one uncertainty that is implied with that. The sequential decision problem then can be formalized with the framework also introduced by Powell, where we would have an initial state that has some forecasts about the prices that are realized. And then exogenous information arises along the time axis. For example, here I make the decision of bidding in the reserve market, and afterwards I get the auction results of the reserve market, of course, and also maybe a renewable update. Then in the next step, I do the day-ahead market bidding, and then I get again information, exogenous information arises, and so on and so on. So that is how you can frame it as a sequential decision problem in this framework that now overarches all the stochastic optimization approaches to solve such a sequential decision problem. So at least that's what Paul frames, that with this now you could either way formulate it as a stochastic, multi-stage stochastic optimization, as a stochastic dual dynamic programming, also from the control domain, or reinforcement learning. And what I wanted to do is I solved this sequential decision problem in a prior work with a multi-stochastic dynamic, with a multi-stage stochastic programming approach for a biomass and a PV power plant, considering the min-max run constraints as well as the maximum ramping constraint and the generation uncertainty. And this looks something like that. So for the stochastic optimization or the stochastic programming approach, I would use some historic data, like the load forecast, renewable day-ahead forecast, intraday forecast, and some forecast errors. I usually, for multi-stage stochastic programming, define a scenario tree. So quantify the uncertainty in such a scenario tree with scenarios as well as the occurrence probability. And then I solve it with a profit maximization over all the scenario paths. It worked quite well. I could actually show that this approach, solving all the markets together, considering a stochastic optimization, has a way higher profit than doing it individually. It increased it by about 25%, so quite substantially for the portfolio that I considered. So PV and biomass together. So we have price and quantity uncertainty here. However, it took like ages. So we've done this for 18 type days, so 18 different scenarios tree, and it took up to 9 hours per scenario tree to solve. And since we also learned in the first talk, that might be reason to apply reinforcement learning to it, because this took a long time. Why did it take a long time? Because you have to define like very many decision variables, but I'm gonna skip that. So the idea, and that's also done in literature sometimes, is to use reinforcement learning to solve this multi-market bidding. So we would give it the same historic market data as observations, and then solve it as a partially observable Markov decision process with cooperative multi-agent setting. So one agent per market, and they learn to bid by cooperating with each other and having a shared reward function. So that's in the future because that's not working yet. I have the individual agents, but they do not seem to cooperate like I want them to. So let's see about that. But then if it works, then they have the profit for each day in the underlying historic data set. And interestingly enough, such a comparison was done in literature before for multi-market bidding with multi-stage stochastic programming and reinforcement learning, as well as stochastic dynamic programming and reinforcement learning. However, currently the applications in literature, there the reinforcement learning setup does not come close to the setup the stochastic optimization uses. So we have way smaller action spaces, for example, or we only choose like one tiny thing, like one action, whereby for the stochastic optimization you have just for the bidding, I think 15 different variables to choose to really construct a bidding curve. And if they are compared, we have very different conclusions on how good the reinforcement learning agent is in comparison to the stochastic optimization. Some literature actually says they perform worse. Some says they outperform the stochastic optimization. And due to this divergence, I'm really interested in whatever my agents come up with in comparison to the stochastic optimization. So to recap that, to simulate future market dynamics and market designs, we want to use agent-based modeling. That was the first point. For assume, we want to substitute the modeler-defined strategy with a reinforcement learning model that then can model strategic bidding and enhance my agent-based simulation. And this is all integrated in the open source Assume toolbox, which will be launched in October. So if you have any interest at all in that, keep an eye out for Assume. The problem is that it's hard to evaluate whatever reinforcement learning made decisions are in this simulation context. We could test it in the multi-market setup. First, we could test it outside of the multi-agent setup by using a single agent and compare it to other solution methods. Or we could test it within the multi-agent setup. Since we cannot compare it to the game theoretic optimum, we can make it at least interpretable and human readable. Also, very much that is planned for Assume. Oh, and that's my backup slide. And that's everything, the overarching, I don't know, storyline that I hope I could make for my PhD. Thanks.
Yeah, very nice. Thanks for the talk. I think we can just set up the competition.
Please.
Yeah, thanks for the very nice presentation. I'm happy you got voted for, because I didn't get to see you post. I was wondering, so there is another project, I think by DLR, or a toolbox called Amiris.
Yeah, it's Amiris.
Context, and is like, what's the difference between these two toolboxes?
Well, that's a very good question. So we're definitely in contact because I also worked at DLR for a brief amount of time, so I know them also personally. Very nice people, indeed. The toolbox has a little different focus, so they're mainly focusing on renewables. That's the first thing. So they look what policy implementations should be in place in order to foster renewables, and then really model their bidding into the market. Assume so far is more focused on the dispatchable, not dispatchable, the controllable generation side. And on the other hand, while Amiris is also open source, you cannot really touch the core of Amiris, so it's not as flexible. You can work with it as long as you provide like input data, and you can also vary this input data, but it's not like you could really get into the core of the model themselves. So we did assume in Python with completely adaptable and changeable parts. We also talked to the Amiris team about collaborating somehow if you could use stuff from Amiris, but since they also programmed everything in Java most of the time, they said, I don't think that would be actually a good idea. And that was their statement, so let's see. But we're definitely in touch to see if we have some synergies arising from the two projects.
Great presentation.
Thanks.
So in the multi-agent reinforcement learning setting, every agent is trained with its own model, right?
Yes.
Yes. So I assume the simplistic assumptions that they made in the initial agent-based simulations, they're done for computational reasons.
Yes.
And in my experience, the reinforcement learning options are very computationally heavy. Mm-hmm. So is that something to consider? Like, does this solve in some way? You compared it against a stochastic optimization, and apparently it works faster, but is this a problem?
So for the agent-based setup that we're currently considering, where we have like 160 learning agents learning on 1 year, it's actually not so much of a problem computational-wise, so we can let them converge within a day. So of course, they have to try out a lot of stuff. And the heuristics, they are usually applied when you want to model like until the horizon of 2050. So if we also want to model with reinforcement learning the horizon until 2050, that would mean that we have to retrain all the time. But the idea is to maybe have then the initial training done. That takes like 1 day. And then we can employ this strategy and only retrain like every X iteration to see like the development over time, so that we can actually then be competitive to also the heuristics time-wise. Because currently, at least the agent-based model that I'm working on during my master's, it was PowerAce from also from KIT, but from a different chair. And there, if you wanted to model like until 2050, it took like 7 days. So it's that to beat. And they did it with heuristics.
Okay, yeah, that seems like a decent workaround.
Yeah.
Okay, thanks.
Yeah, so I was wondering, you have the original setup of these heuristics for people who download based on pricing or make their decisions. Now, I would say indeed this reinforcement learning approach is a lot better, but since you're modeling actual behavior, is it realistic in that sense that people would indeed reinforcement learning method?
I mean, if you look on how many people or how many companies are actually applying already algorithmic trading, you could say that at least for these big companies, it's realistic that they also behave similar to reinforcement learning agents. But of course, the little biomass power plant on the farm X epsilon, that would not apply such an algorithmic trading mechanism unless they're dispatched by someone else. But it's not necessarily about reproducing human behavior, but about testing out then new market designs in case of flaws. If I want to implement market design change X, epsilon, does that have any impact on the way I can exert market power in the market? So we would still not be able to project the future in that sense by using reinforcement learning. So still an optimal solution that we most likely won't see there, but it at least gives a better indication about what we could expect from market design if everyone would be as smart, so to say. Do I have time still? Okay. Or did I miss someone there, or why were you pointing this? No? Then go ahead.
Thank you so much for the nice presentation. I enjoyed the poster presentation yesterday also.
Thanks.
But I remembered a new question because I'm really interested in the topic. So you want to test for finding flaws in the market design, like for instance, someone abusing market power or doing in-tech payment, right?
For example.
My question is, in your multi-agent setup, where agents probably know about each other, like, they have like a common critic for me. This could explore how they can collaborate to like against the system, or so to speak. But wouldn't it also be plausible that maybe if even they exhibit competition, this could show more flaws in the system than if they exhibit like collaboration?
I wouldn't necessarily say that giving them a central critic is collaborative reinforcement learning then, in that sense. I'm not totally sure on the distinction if I give them this central critic, but the critic only says it, would that action be good, in a sense, assuming having knowledge of the other agent's behavior. So that's why you say it's cooperative, right?
Sort of, yeah.
Okay, so then let's stick with somewhat they are cooperating, whether or not it's cooperative reinforcement learning, so to say. And your idea would be that if I let them compete, so without having this shared knowledge, that then they could even exert more of the market design's flaws. That would be the idea.
Hypothesis rather than idea. It's yeah, that's what I'm supposing. Yeah.
I mean, it's a good question that I cannot think of an answer from the top of my head. Would be interesting. The problem is why we use the central critic, though, so some kind of shared information, is that otherwise, I think we discussed it yesterday, right? That otherwise the problem wouldn't be Markovian, because then the agent does not know why this decision, okay, maybe then for the rest of the room, usually you have to have the case that if you make the same decision again in the same state, that the outcome has to be the same. If I have a multi-agent setting and I only give it like information, global information about the states, and the agent does not know about the behavior of the other agent, it could actually do the same action again, but since the other agent behaved differently, then also my reward would be differently. And that is not good for reinforcement learning, then it does not converge. So that was the reason for the central critic in that sense. Really deep into the reinforcement learning implementation now, though. And yeah, but I really have to get into your question. I'm not too sure about whether or not it would change, but we cannot ditch the central critic. So I also wouldn't know how to evaluate it, to be honest. But it's a good point. Thanks.